So, everyone, welcome back again. Okay. In the last session, we have covered different variant of the K epsilon model, right? The standard K epsilon model, the realizable K epsilon model, the RNG K epsilon model, right? So, every model then needs the boundary condition. These are partial differential equation, like any other partial differential equation. This needs boundary condition, right? So now we'll study about what kind of boundary condition we need to solve this model, right? Normally, for a problem, what kind of boundary condition you are encountering? What kind of boundary conditions? Forget about turbulence. In normal in a flow problem, what kind of boundary condition you are encountering? At the solid wall, no slip boundary condition, right? Then no penetration boundary condition. The fluid cannot penetrate the solid wall. That's fine. Then mass flow inlet boundary condition, right? If there is a pipe, there is certain amount of mass is coming. We have the mass flow inlet boundary condition, right? Similarly, we have some outlet boundary condition, pressure outlet, outflow, right? So now the things is that there may be a solid boundary, right? Where there is no slip condition, no penetration condition is satisfied, or there may be an inlet or pressure outlet boundary condition, right? At each boundary, we need to define the boundary condition for the K and epsilon apart from the velocity, right? So now come to the boundary condition details, okay? For K and epsilon, right? So the boundary condition normally at the inlet boundary, they define in terms of the flow Reynolds number, right? So in terms of what? Intensity, dissipation, mixing length, these are the input. Normally one give, when you apply the inlet mass flow inlet, you have to prescribe what is the mixing length, what is the flow intensity, right? So where you get these things? The right hand thumb rule is to calculate the Reynolds number at the inlet. Based on the Reynolds number, there are some empirical correlation. You can calculate the intensity Reynolds number to the power minus 1 by 8. The coefficient is 0.16. This is the intensity of the thing you can define at the inlet. Other thing is that you can prescribe the mixing length at the inlet. The mixing length is normally 0.07 times the characteristic dimension, right? So you can define the height, or if it is a non-circular section, the D stands for the hydraulic diameter, right? So this is the inlet boundary. Similarly, this is the boundary condition for the K and epsilon, right? At the inlet, N means stands for the normal direction to the boundary, right? So there are several methods. Once you calculate the intensity, from the intensity you can calculate your average velocity intensity square. If you do it, you will find the kinetic energy. At the inlet, you can provide the kinetic energy boundary condition. From average velocity into intensity, you multiplied it, you square it, you will find the dimension of K, and you can specify the kinetic energy, turbulent kinetic energy, right? Similarly, epsilon normal to the wall, you can specify. Once you calculate the turbulent kinetic energy, calculate the mixing length, you can specify the epsilon at the inlet. Clear? So suppose there is a pipe flow, right? So you have a pipe or you have a geometry where flow is coming, right? Based upon the velocity, diameter, you can calculate the Reynolds number at the inlet. From the Reynolds number, calculate the intensity, right? Once intensity is known, you can use the intensity and average velocity to calculate the K, epsilon. So for inlet boundary, you can calculate K and epsilon boundary condition, right? Good. Similarly, for outlet, there is a geometry, it has an outlet. So simply do what? At the outlet, keep K and epsilon equal to 0. Turbulent kinetic energy and epsilon at the outlet, you can fix it to the 0. Clear? These are the outlet boundary condition, right? Apart from inlet outlet, there may be a symmetric condition. Yesterday we simulated the flow across the cylinder. Then in the far field, right, while we are simulating flow across a cylinder, we take a domain. This is the cylinder, the top and the bottom. So this where you are applied the symmetry boundary condition. Symmetry means the gradient of the flow field quantity, they are vanishing, right? So any, suppose I am taking its normal direction, any del phi by del xn, they are supposed to 0. The gradient is vanishing at the far, right? So at that condition, the gradient also for the kinetic energy and dissipation, they should also vanish, just like a velocity, temperature, or the symmetric boundary, the gradient must vanish. Clear? The boundary condition for K and epsilon at the inlet, at the outlet, at the symmetric boundary. It is clear? Now come again the universal nature of the graph, right? So this is wall y plus, right? Again, y plus is a magnified lens to see the wall normal distance from the solid wall, right? So y plus is a non-dimensional variable that gives represent wall normal distance, right? This is u plus, again with the friction velocity, right? We have non-dimensionalized the shear velocity. Clear? We calculated the u plus, we calculated the y plus. So yesterday during the law of wall, we have noticed somewhere they follow the universal profile. The variation follow a universal profile. What are the universal profile? If y plus less than 5, then they are linear. U plus equal to y plus. If it is y plus greater than 30, they are logarithm, right? So we are plotting in a log scale. That's why the linear relationship is a curve and the logarithmic relationship is a straight line. Okay. So then what happened? This is the DNS data. Okay. They did the DNS. They resolve all the scale Mozo. Okay. This is a famous group from the Stanford, I guess. They did the DNS simulation. They did the DNS simulation and feed the curve, right? Starting from the all y plus from less than 5 or 1 to the higher y plus up to 1000. They feed the curve, right? So this is how the curvature is going, the linear profile. This is where the logarithmic profile. Then there is an attempt to find a equivalent fitting in the buffer zone that uniformly describes the flow, because in the buffer zone nothing is defined, right? So then the wall function came into play. Okay, so let's see what are the wall function. Again the same condition, we have to make the velocity, tangential velocity dimensionless with respect to a shear velocity u tau, right? So now from the flow of the Moser, 1990 presented the graph between the tangential velocity and its distance from the wall to bring universal the distance of velocity expressed in terms of dimensional quantity u plus and y plus. Clear? Then again the wall normal distance, they are also non-dimensionalized, that gives the y plus, right? How to calculate the shear velocity, right? You know the mean flow velocity from the previous iteration when we are solving in the CFD. You know the mean flow velocity. Once the mean flow velocity is known, you can calculate the wall shear, right? From the mean flow, you can calculate, how calculate? Mu del u tau average by del xn, right? This term you can calculate at the wall. Suppose this is a solid wall, the flow is moving. So you can calculate the velocity gradient with respect to normal direction, right? Then multiplied with viscosity, this will give you the wall shear, right? Once wall shear is known, you can calculate u tau, right? Once u tau is known, you can calculate y plus, you can calculate u plus, right? Then The idea is if y plus less than 5, then u plus equal to y plus. If y plus less than 30, then there is a logarithmic relationship. Then subsequently in the buffer zone it tells nothing, right? Then subsequently, okay, we have discussed these things yesterday. Again, we will come back to this picture. Okay. Subsequently, Spalding, right? He prescribed a mathematical functions that uniformly fits the curve from the low Reynolds number region to the high Reynolds number region, right? The u plus as a function of y plus, or y, or vice versa, the y plus as a function of u plus. For y plus in the range of 0 to 300, he fit it y plus as a function of u plus, right? And how this function looks like, right? This is the curve. That fits well with the experimental data, right? Then what is the difficulty in obtaining those u plus, y plus, how they are implemented? Yesterday there was a lot of doubts to clarify those things, how these things are calculated, what these things are looks like. Again, look at the zoom section in the boundary layer. If it is not the viscous sublayer, the velocity profile is nonlinear. If it is not the viscous sublayer, the velocity profile is nonlinear. But for the second order finite volume based scheme, right? Once we calculate the gradient, how we will calculate the gradient? With the linear profile approximation, velocity at this point minus velocity at this point divided by vertical distance between this point. That is the way to calculate. But is it correct? Because my velocity profile is nonlinear. Maybe if I have a point close to this here, somewhere here, then if I take a linear approximation, that is correct. But I don't have sufficient computational resource, right? That's why I'm putting the point somewhere in the top. The distance, the difference between the point here to here, I am taking as the distance. Then taking the velocity from here to here. Whether although the velocity variation is non-linear, I assume it as a linear and taking the difference. That's why it's an incorrect way, right? Then there is a subsequent method to compensate, okay, the error in the linear profile approximation. What is that? That is the friction or eddy viscosity will save at the phase center, right? Suppose this is my computational center, right? Every computational center, once you generate the mesh, it has a cell phase, right? Clear? It has a phase center, it has a cell center. So phase center to cell center distance is known. Clear? So at the cell center, okay, they save the eddy viscosity, right? For while y plus calculation, additional we have to save the viscosity, eddy viscosity information at the phase center. For each phase, there is a specific eddy viscosity. How it looks like? Let's come to the next slide. Okay. If my first cell center is in viscous sublayer, then how my tau shear stress looks like? They looks alike to this formula, right? So UP is the cell center value, right? This is my boundary value. If no slip condition, this boundary value should be 0, right? So cell center value minus phase center value divided by the distance between cell center to phase center. That's supposed to be the correct one, and multiplied by the dynamic viscosity. That will give me the tau omega. If my point, the cell center and the phase center distance is extremely small. But if it is higher, what to do, right? If it is higher, we'll use the same formula, but instead of the dynamic viscosity of the fluid, we'll put some wall viscosity or the friction viscosity, turbulent viscosity. This information, okay, will save at this phase, because suppose this is cell is there at the corner. It has two urgent different phases. One cell is connected to two phases. This distance may be different from this distance, right? But if we set the turbulent eddy viscosity to calculate the tau omega at this center, then this will give the same value. It will be used to calculate just wall shear at this point which is incorrect. So instead of solving or saving the eddy viscosity at this point to calculate the wall shear at corresponding phase center, the eddy viscosity is set so that for a particular phase center, the distance from the cell center is unique. Then accordingly, if we save the viscosity over here, we know the distance, we know the velocity difference. If we know the eddy viscosity at say known eddy viscosity at the phase center, we save it. That compensate the things. Compensate means although it approximate the linear profile for the velocity, it enhances the viscosity, eddy viscosity, so that it looks like it is a nonlinear profile. Clear? So now it looks how it looks like. My tau omega is rho u tau friction velocity, because tau omega is rho u tau square. So I keep one friction velocity, the other friction velocity I put it tangential velocity by u plus, right? Then I put the definition of the u plus in the log layer. Okay. Then after doing these things, I got this formula. U tau is nothing but my cell center value minus the phase center value. This one u tangential velocity, right? Now I got this formula. Okay. Then what I will do? Then I will divide it. In case of my first cell center is not within the viscous sublayer, the idea is to evaluate this term. This term is unknown, right? The eddy viscosity you don't know at the center. You know the mean velocity. You can differentiate find the mean velocity at the cell center and the phase center. You can find the gradient, but you don't know these things. These things you need to evaluate first. Okay. Then to evaluate this thing, how these things looks like? This things looks like this rho u tau xp times this is the logarithmic profile. Okay. Means if you know the wall y plus value, you can evaluate the friction velocity, right? Or if you divide it with the density, it becomes kinematic kind of eddy viscosity that saves at the phase center, right? Then if we add both, we don't know whether it is lamina, so at the whether it is in the viscous sublayer or out of viscous sublayer. In a generic sense, we can add both turbulent eddy viscosity and the laminar viscosity to make it equivalent viscosity, tau wall viscosity, right? We can make it equivalent or wall viscosity, right? Then put this expression, okay? Then the wall viscosity looks like it's supposed to be 0 if y plus less than 11.225. Where this 11.225 came? Here. Yeah. These are two completely discontinuous functions. One is straight, one is curvature. Somewhere at the center, we have taken 11. This is 10, 11.225. This is the thing where they are taking the short thing, right? So instead of going discretely 5, going more than 30, in between things are not known. So what commercial software do? If it is less than 11.225, you do this. If it is more than 11.225, you do that, right? Then they treat it, if it is less than 11.225, they take it linear approximation. If it is more than 225, they do it this approximation. Logarithmic approximation. Clear? Then again to calculate the u tau, okay, you need y plus. To calculate y plus, what you need? Again tau omega. This is again a circular thing. To calculate this y plus, you need tau omega. To calculate tau omega, you need y plus. Okay. This is again a coupled system. Okay. You cannot solve it if you put each other. You will get a form. Okay. You will get a form, this form of equation. If you put each other, okay, to finally eliminate this u tau, you get the equation for y plus in this form. This is a nonlinear equation, right? Some y plus time logarithmic equation. So You cannot simply solve it like a linear equation. You cannot solve it. You need some iterative scheme like Newton-Raphson method, some good initial case to solve this algebraic equation first, because these terms are known. The velocity at a boundary, this molecular diffusivity, this von Karman constant, the distance of the cell center to phase center, this term is known, right? This E is known. These two value to solve this nonlinear logarithmic equation, you need iterative process, which is quite computationally expensive. To avoid those things, the commercial software, instead of calculating the y plus, they calculate y star, right? Y star is what? This is another way to non-dimensionalize the wall normal distance. Analog to y plus, again if it is non-dimensionalized with y star, the universality nature of the profile remains alike, but the way of non-dimensionalization changes. Earlier what? How we non-dimensionalize? To y plus we non-dimensionalize in a way u tau we need it, which you don't know. To calculate u tau we need a friction velocity. That is also different. So this coupled method to calculate y plus is quite complex because u tau is really not known, right? To avoid these things, the non-dimensional is based on the new non-dimensional group they introduced, that is called y star in ANSYS Fluent and many other software. Subsequently, from y star you can calculate the y plus, right? So now come y star. How y star is defined? The non-dimensionalized. So Kp is what? The kinetic energy at the first cell center. Suppose this is okay. These are my solid wall. These are my computational cell. At the cell center, once I solve the differential equation, I have from the previous iteration or previous time step, this shapes everywhere the value of K, Kp, that I call K at kinetic energy at the first cell. Here, so you take the from previous time step or the previous iteration, you take the value of the K, you put it over here. This is known. C mu, either it's a constant or it's a function that depends upon the strain rate or mean vorticity. We have defined earlier, depending upon the model, whether it's a standard capsule model or RNG model, you can calculate C mu. Rho is known. Xp is the distance between the wall to the cell center, that is also known. Mu is known. Now this y star is easily computable thing compared to y plus. Y star is easily computable thing, right? You calculate y star. Similarly, u star, there we have non-dimensional with respect to what? U divided by u tau. We don't know u tau, right? Once you solve it, then we'll get the u tau. Before solving, you don't know. Here we non-dimensionalize u tau. Up is my cell center value. Suppose you are solving kinetic energy at the cell center. You have also information about velocity at the cell center. So velocity at the cell center, kinetic energy at the cell center. You solve it and tau omega, the wall shear stress, you save it from the previous time step. Now this u tau is known, y tau is known, right? Now come to the thing. So again, if y star is less than 11.225, your profile looks linear. If y star is less than greater than 11.225, your profile is log, right? If you take this and put it over this definition, right? Instead of y plus, you replace it with y star, you'll get a expression like this, right? If it is in the laminar zone, the what is the wall friction viscosity? 0. We don't have any additional because I resolve my grid sufficiently that there is no turbulence. My profile approximation is linear, right? So this terms goes to 0, right? Then if it is more than 11.225, means the height is little bit higher, then based upon the value of the previous iteration or previous time step, I calculate the viscosity, eddy viscosity at the wall, right? Once I calculate the eddy viscosity, where it is eddy viscosity is going to use? Where I am going to use the eddy viscosity? In the current time step, I am going to use this eddy viscosity to calculate the shear stress. So once this is calculated, I am going to use that to calculate my shear stress. Now shear stress is updated, right? In the next time step, I will use the previous shear stress value, right? Again updated the eddy viscosity. Now it is clear what is wall function. So wall function don't change the velocity explicitly. It calculate based upon the fitting function. It calculate a wall viscosity. Save it at each phase center, not cell center. It saves the wall viscosity at each phase center, right? For each phase value, you are calculating the shear stress. Maybe flow at this here. You need tangential component velocity, this velocity minus this velocity divided by the distance into shear stress. That time you can use the shear stress, the viscosity of the wall that is stored at this location, right? If you are calculating shear stress at this point, you will use the viscosity value that is stored at this location, right? To solve the transport equation, you use the eddy viscosity stored at which location? If you are solving the transport equation, cell center. Okay, only to calculate the shear stress, you will use the viscosity, eddy viscosity that stored at the phase center. Otherwise, to transport equation, you use the eddy viscosity stored at the cell center. Now it is clear what wall function is doing. This is not explicitly mentioned anywhere in the documentation or book, anything. They just everywhere, every document, every piece of book you follows, what they did, they just mention this profile and leave that on. Okay, y plus 5, y plus 30. They don't explicitly tell you how you write your own algorithm or code or modify a standard code to do this thing, right? But if you are a developer, you are developing code for the open source software like Code Satron, what you call open form, okay? Then you need to know, right, how these things are implemented, or in ANSYS Fluent, how these things are implemented. So this is the way. Once you do coding, your most of your idea logic, you will get it. How this is implemented, how the equation looks like, what is the difficulty in solving those equation, what is the alternate form. People have difficulty in solving with y plus value. That's why they use the y star value. This is another way of non-dimensionalize it, because to solve the y plus, we need a additional non-linear equation in terms of the linear and product of linear and logarithmic value, which you need Newton-Raphson method with some guess value. You go on finding the things, right? That's why instead of avoid those things, you now solve the y star, u star. Clear or any doubt? It's clear. Yesterday there was a demand to cover those things. I promise today I will cover it. Hope now it is makes sense. Clear? Now we use the velocity wall function, right? Again, the velocity, this wall function do not explicitly change the velocity. They do not change the velocity to put the velocity in logarithmic scale or linear scale. Rather, they calculated some equivalent eddy viscosity and save it at the phase center, that subsequently used to calculate the wall shear, which is used to calculate the wall shear. Clear? Again. So now the boundary condition, we need boundary condition for K, we need the boundary condition for the epsilon. So what velocity boundary condition we used? At the wall, what velocity boundary condition were used? No slip, wall we fix it at 0. Okay. We modify the viscosity such a way that the first layer velocity will be modified. Clear? Tau omega is equal to mu wall del u by del xn, right? This is 0, right? the wall distance is known. Suppose this is dp, wall to cell distance. So tau omega is now known from the wall function, right? So tau omega is this term is known, mu omega is known. So this term will be my velocity as cell center minus 0, no slip condition is put over here, divided by dp. Now the first cell center value is how much? dp tau omega by mu omega. Right? So in the high Reynolds number approach, okay, again one important thing, right? The CFD solver do not solve the velocity profile directly from the boundary. What it mean? Clear? Okay. Suppose this is a pipe flow condition. I generated the mesh. Right? These are my solid boundary. Clear? Once I am in the high Reynolds number formulation, the matrix solver, they solves velocity only for the internal cells, not the cell adjacent to the wall boundary. Where they get the velocity for the wall boundary? That just we discussed. Wall shear stress, they equate the calculate the wall shear stress from the previous iteration, then they mu wall del u by del xn. This del xn is nothing but this is mu omega, del u nothing but up minus 0 if it is a no slip condition divided by distance. Then up first cell velocity become how much? Tau omega dp times, correct me if I am wrong algebraically. Correct. So once this internal velocity will be calculated from your CFD solver, these velocities are updated from this formula in the high Reynolds number approach. They don't solve the entire equation up to the wall. The first adjacent layer up to the wall, the velocity is corrected from the wall shear, that is effectively by the eddy viscosity information that solves at the wall, and the velocity, cell center velocity is updated. This updated velocity, they influence the subsequent cell velocity in the next iteration. When you are solving the next subsequent time step or subsequent iteration, the matrix, this velocity is influence this velocity, right? So from this value, this get updated, from this value, this get updated, and iteratively this process continues. Clear? So, but if it is a low Reynolds number model, now again high Reynolds number and low Reynolds number model. If it is a low Reynolds number model, the governing equation, the velocity, everything, they are solved from this to this cell. All the cells, governing equations are solved in all the cells. If it is a high Reynolds number model, you are using any wall function, the governing equations are not solved in the wall adjacent cell. They solve everywhere inside the domain except the wall adjacent cell. But if it is a low Reynolds number model, we will decide what is low Reynolds number model subsequently. Then the governing equations are solved throughout the domain, all cells throughout the domain. Things are clear? What is high Reynolds number model? What is low Reynolds number model? For high Reynolds number model, governing equations are solved within the interior grid point, not grid adjacent to the wall. For the low Reynolds number, everywhere. Will come what is low Reynolds number model and how it looks like. Clear? So now Again. So we'll cover few things. At the wall, ideally, the kinetic energy is supposed to be zero. Once fluctuation is known, kinetic energy is supposed to be zero. Again, there is a condition that Neumann condition, the gradient of the kinetic energy is supposed to be vanish at the wall. Okay, that book by Durbin, they describe two conditions. Which one is the appropriate condition, right? Most of the CFD solver, they use the second condition, that is the wall normal gradient of the kinetic energy, they must vanish at the solid wall. Okay, so this condition, they vanish at the solid wall. They have given a lengthy derivation in the Durbin and some justification why to use this condition, not this condition. After the expanding into second order Taylor series with mathematical calculation, but the Neumann condition, the wall normal gradient of the kinetic energy must vanish, right? So again, alike to the Y star, U star, we have a K star also, non-dimensionalized version of the K, right? Then how it looks like, this sum of the K star and Y star, they have some universal profile, right? Based upon up to the linear layer up to 5, they bear a curve like this. In the log layer, they have a curve like this where there is some deviation. Okay, you find it in the, these are the DNS data. This is the Wilcox book. They have the theory, right? This is the K star and Y star universality diagram. It is not that universal like the velocity case. We can see some deviation from the DNS data to the theoretical result, right? Similarly, for epsilon, we see the things. Although we have taken 11.2 as the mid region to join the two things, but still, if you don't precisely do the meshing, you are lying in the buffer zone, your epsilon and K computation will give deviation. Here, they don't have information what to do. Okay, if your grid lies this region, right? 9, they don't have any information what to do the K. They don't have the information what to do the epsilon, right? They match very good if it is less than 5, they match very good if it is more than 30. So, although the commercial software, they do some kind of blending to give you the equivalent result even if your Y plus is in the buffer zone, but for correctness, the user need to ensure either it's a low Reynolds number mesh, Y plus less than 5 or Y plus more than 30. Don't put it in a buffer zone. Lot of information will be erroneous because in that zone, although the velocity profile will be corrected, but K and epsilon, those are very different from the DNS data. Okay, then just like from this curve, just like we fix a equivalent function for velocity, they also fix the equivalent function also for K. If it is less than 11.225, K should be looks like this, otherwise K should looks like this, logarithmic region, right? For standard K epsilon model, epsilon is not defined at the wall. You cannot integrate the epsilon equation up to the wall. Epsilon is not defined over here, right? Then what value of epsilon you will use? So to do that, right, near the wall region, right, we have to come to the production. All other terms they vanishes because of the low velocity. If you go to the viscous sublayer in the governing equation, the velocity will vanish close to the wall, no slip condition prevail and velocity is extremely small, right? The production should be matched with the dissipation close to the wall in the viscous sublayer. So if you equate, you find the expression for the production, then you will find the production terms looks like this. Like, then from the production you will equate the production to the dissipation, right? Then you will find the dissipation term. The dissipation will give you an equation like this, right? So in the first cell center, you have to prescribe the value of the epsilon. The solver will compute the epsilon, the intermediate or the interior grid point. But the value of the epsilon you have to provide at this hash grid point. It is not integrable up to the wall. You cannot provide the epsilon boundary condition at here and do the solution. It is not defined. Epsilon is not integrable up to the wall. You have to prescribe in epsilon at the first cell center from the algebraic relation and solve it for the interior grid point. It clear? The boundary condition K, epsilon, wall plus, these are clear. So this is called what we discussed. This is called standard wall function. There are different variant of wall function. Something called standard wall function, enhanced wall function, scalable wall function, non-equilibrium, or the two-layer wall function. There are package of wall function is there, right? What we discussed just, that is called standard wall function. There is some other wall function. What they do, they use the exponential function to blend the u plus value between the viscous and the log layer. They use the exponential function e to the power tau plus e to the power minus 1 by tau. This kind of wall treatment is called enhanced wall treatment or enhanced wall function, right? What is this tau? This is tau again is a function of y plus, right? If you know the y plus, you calculate the tau. Once you know the tau, you find exponential of the e to the power tau, e to the power 1 by tau. Okay, you calculate the log in the log layer y plus value, in the linear layer y plus value, in the log layer y plus value, the viscous layer. This is given by this. This is a function of y plus only, and there are some parameter alpha. In the log layer, they are the function of y plus alpha, beta, gamma, right? Where it is used in a non-equilibrium flow. In the boundary layer flow, normally in the Prandtl boundary layer or what do you call Blasius boundary layer, there is not any pressure gradient, right? Within the boundary layer. But if you have any pressure gradient within the boundary layer, then this function relationship is different, right? So this function relationship is calculated from the pressure gradient. If there is not any additional pressure gradient, alpha becomes 0. If there is not any heat transfer, beta is going to 0, right? There are some other parameter Cp, based upon the boundary condition, where it's a conducting boundary, heat is injected, or there is a pressure gradient, etc. If you put alpha, beta, gamma equal to 0 for a simple flow in a pipe, etc. This enhanced boundary treatment becomes similar to your standard wall function. Enhanced wall function equivalent to your standard wall function. If alpha, beta, gamma is equal to 0, means this parameter, in absence of any external pressure gradient or in absence of any heat injection, this parameter is going to be 0. And what will happen? So this is equal to 0. And your enhanced wall treatment is equal to your standard wall treatment. But if you have any heat injection, if you have any pressure gradient, the solver will consider those things to calculate your enhanced wall treatment. Now it is clear? Clear? So now boundary condition for the K epsilon model is now clear. So this is the difference between two wall function. The first one, the dotted line is the DNS data, right? The standard wall function is giving some kind of discontinuity at 11.25. This is some kind of discontinuity, right? This is coming over here in the zoom scale. When I zoom the scale, we find the discontinuity over here somewhere, right? But this enhanced wall function, they blend it continuously. There is not any discontinuous thing, right? They blend the function continuously. So that's why you get a continuous function that match well with the DNS data. Only deviation it will give here y plus 5 with this region, right? So enhanced wall treatment is bit preferred. When you don't know there is a curvature boundary, maybe external pressure gradient, etc., you can use the enhanced wall treatment. Clear? Well, y plus is clear. What is y plus? What is y star? What is wall treatment? It is clear. Now let's come to the low Reynolds number model, right? What I told in the high Reynolds number model. What is the high Reynolds number I told you? The high Reynolds number model, the flow variable is not solved up to the last grid point. It is solved here, 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 right? It is not solved here. But it is algebraically calculated here based upon the wall function. But often that is not a correct approach, right? That's why when I compute the DNA, compare the DNS data with your velocity profile from your Epsilon model using the wall function, you'll find it is overestimated. Your wall function artificially trigger the turbulence. Although the flow is laminar, it will artificially trigger the turbulence by excessively predicting the Reynolds stress in the first layer, because you are not solving, you are algebraically predicting it. Just you can see, this is my DNS data, right? This is the standard Epsilon model, okay, or Epsilon model. They artificially overshoot the data. To do that, to bring that data naturally, with CMU there is additional function they are multiplied. Additional viscosity, to calculate the wall viscosity over here, there is additional function they are multiplied so that they damps out the data. They have become the close match. Where this additional function, how this additional function looks like, let's come. So this is my low Reynolds number Epsilon model, right? You can see this low Reynolds number Epsilon model, instead of epsilon I am solving, there is additional new version of the epsilon, that is called epsilon tilde, right? This, what is the epsilon tilde? This is epsilon minus d. Okay, this d e are the ad hoc function. I will define what d and e, but again the form of the k equation they remain unchanged, right? The form of the epsilon equation they are changed. There are 2-3 new things appear. What are the new things? F mu, which is unknown, the damping function, right? There F1, F2, right? This D, E, these things are appear, additional equation. But the good thing is that this equation integrate up to the wall. Your grids are very fine near the wall. They integrate up to the wall. Okay. To honor the wall effect, okay, near the wall, the flow should be laminar in the viscous sublayer. To honor that effect, the epsilon is not defined adjacent to the wall, so it must be vanishes, right? To honor that effect, they put some additional damping function over epsilon so that it should be vanished by the time the flow approaches the wall. So they define epsilon minus epsilon d, right? But how this d, e and wall fb wall looks like, there are again 30-40 models are there to do the things. This is not a simple thing. I'll show you. Okay, there are K epsilon Launder Sharma model is there. There are Bram Lamos model is there. I'll show there are almost 30-40 variant is there. I'll provide you a table where I have in the literature I have saved which model, what is the definition of D, what is the definition of E, what is the definition of F mu, what is the definition of F1, and what is the definition of F2. I'll provide it. Okay, this is a functional definition. There are almost 20 to 30 variants there. So nothing is simple. There is not any unifying model that helps to get the thing, but mostly the Launder Sharma model they validated for most of the cases. Okay, then if someone tell you K epsilon Launder Sharma, it's a high Reynolds number model or it's a low Reynolds number model? Low Reynolds number model. Now it is clear what is low Reynolds number model. The low Reynolds number model they integrate it's up to the wall, means they solve the flow field throughout the domain. High Reynolds number they don't solve it in the adjacent cell near the domain. rest where they solve it, right? But the issue with the low Reynolds number model is that you need additional damping function, you need additional parameter. That's again problem specific. There are C and some other model and Landa-Sharma model. There are 20-30 models are there. So earlier it was in the ANSYS Fluent version available. Now they remove it from GUI. Although this is available in TUI, text user interface, you can switch on it. But the ANSYS stop providing any documentation regarding this in the public domain because they stopped developing this model long back. But from the experience, some of the model, low Reynolds number model, they match quite fine with the DNS data. Okay, just like I have shown you over here, they match quite fine with the DNS data. Okay, and the results is over here. This is K Epsilon Landa-Sharma model, and this is DNS data. Okay, this with Parvez Moin's data. You can see the Landa-Sharma model matches fine with the DNS data U plus Y plus. Up to at least 100 they match fine. Clear? So here we can stop the session for another break. Then we'll get back with the K omega model. That is will be our third session for the today. We'll get back with the K omega model. Okay. Thank you for your attention. If you have any doubts regarding the valve function or the boundary condition for K epsilon, you can ask it for this session. Any doubts are there? You have any doubts? Yes, if it is low Reynolds number model, means the solver is solving the equation up to the valve. If you don't switch on the low Reynolds number model, by default it will use the valve function to calculate the first grid velocity, and subsequently it will solve the solver will solve the velocity for the intermediate grid points. Yes, I will share it. I will ask the admin office to share it with everyone in the email. Done with doubts? Thank you everyone. Let's meet in the next session.